On a cold Chilean summit in the late 1990s, two rival teams tilted their telescopes toward the same fragile flicker, a dying star in a galaxy halfway to the horizon of time. Typea supernovae are nature's precision flashbulbs. White-hot, near-identical explosions bright enough to outshine their host galaxies, brief enough to mark an instant on the universe's clock. Measure how fast that flash fades and you know its true wattage. Compare with how faint it looks, and distance falls into your hands like a well-worn map. Night after night, the astronomers gathered light curves, plotting brightness against time, expecting a simple story. The farther the supernova, the dimmer it should appear. In lockstep with a universe coasting under gravity's gentle break. Instead, the distant beacons were even fainter, farther than any coasting model allowed. It was as though the road between us and them had stretched while the light was en route, as though the cosmos had pressed an accelerator no one knew existed. Here was acceleration writ in candlelight. No extra stars, no hidden dust could mimic the effect across dozens of explosions, each in a different direction, each offering the same quiet confession. Space itself is swelling faster with age. The discovery did more than tweak a number. It added a new actor to the cosmic cast, one that pushes rather than pulls, invisible yet in command. So by timing the fade of far-off supernovae, astronomers learned that the universe is not just expanding, it is speeding up, propelled by an unseen pressure that outweighs every galaxy's glow. Long before the first stars kindled, the newborn universe was a glowing fog of plasma. Sound could travel there not through air but through light-coupled matter. Every pressure wave that rang through that early fireball left a spherical imprint, like ripples etched into cooling glass. When the fog thinned and atoms formed, those ripples froze in place at a fixed scale, about 500 million light-years across in today's stretched units. It was eons later, galaxy surveys trace that fossil rhythm. Map a few million galaxies, measure how often pairs sit that magic distance apart, and a subtle swelling appears in the statistics, a whisper of primordial thunder. This standing shell, called a Baryon-acoustic oscillation, is cosmic masonry. Its size is set by physics so early and so simple that we know the ruler's length to better than 1%. Because the shell's span is fixed, its apparent size at different redshifts reveals how much the universe has expanded since each epoch. Projects like EBOS and the newer DESI have carried this ruler across cosmic history and found the same story the supernovae told. The scale of the universe between then and now has grown faster than gravity alone can explain. No single telescope, no single method, whether candle or ruler, stands isolated. Together they harmonize on a single unsettling note. An unknown energy pervades space, urging every meter to become something more. The ripples of primordial sound embossed on today's galaxy web act as a standard ruler. And they, too, insist that a mysterious agent is stretching the cosmos at an ever-quickening pace, confirmation writ not in starlight, but in the arrangement of galaxies themselves. Hold out your hand and imagine you have removed every grain of matter, every wandering photon. What remains should be nothing at all. Yet Einstein's equations allow this nothing to carry energy, a uniform pressure we label lambda, the cosmological constant. Astronomers measure its density at about 6 protons, mass spread through a cubic meter of space. Scarcely a whisper, but enough, across cosmic volume, to overwhelm gravity's pull. Here's the puzzle. When physicists add up the restless jiggle of quantum fields, the zero-point energy that no vacuum can shed, they do not get a whisper. They get a roar, a value larger than the observed lambda, by a factor written not with zeros, but with exponents. 10 to the power 120. It is the worst numerical mismatch in all of science. A budget sheet off by more cash than atoms in the observable universe. Why is the measured vacuum so gentle when theory predicts a storm? Some suggest a hidden symmetry delicately cancels almost the whole tally, leaving the slight surplus we observe. Others invoke a multiverse lottery. Countless regions with random lambda values. Life emerging only where expansion is slow enough for galaxies to form. Ours simply won the existential draw. Neither answer satisfies everyone. Both drive new mathematics, new experiments, New late-night debates in coffee-smelling corridors? The same emptiness that lets light pass through glass carries a faint but unstoppable pressure. Yet our best theories predict a force unimaginably stronger, leaving us with a paradox as gaping as the cosmos itself. Suppose the vacuum's push is not a fixed constant at all, but the breath of a sleepy field, quintessent, rolling ever so slowly down a shallow hill in energy space. In this picture, the field's pressure is described by a single number, W, the ratio of pressure to density. A true cosmological constant has W equals -1. Quintessence nudges that value slightly higher, meaning its strength can wax or wane as the universe ages. Telescopes already probed this possibility by comparing galaxy cluster growth, supernova yardsticks, and the frozen ripples of baryon-acoustic oscillations. Observers have narrowed W2 within a few percent of -1, but not exactly on the mark. A gentle deviation could hint that dark energy is evolving, perhaps destined to fade and let gravity slow the expansion after all. The equation can bend the other way too. If future data reveal W dipping below -1, we enter the realm of phantom energy. Here, the vacuum's repulsion strengthens with time. Tens of billions of years hence, the scale factor would diverge toward infinity in a finale called the Big Rip. Long before that ultimate tearing, galaxy clusters, stellar systems, even molecular bonds would succumb, each unstitched in turn by the ever-amplifying stretch. Current uncertainties still leave the door open to each storyline: steady lambda, graceful quintessence, or the catastrophic phantom. Next-generation surveys aim to tighten W's leash, turning whispers in the data into verdicts about destiny. Whether dark energy stays constant, ebbs gently, or swells toward a cosmic undoing depends on a single number, W, and the universe is keeping that final decimal just out of reach for now. Stand on a quiet country road and watch two cyclists pedal side by side. One rider coasts in familiar Newtonian fashion, speed fading under gentle friction. The other impossibly glides faster the farther she travels. Dark energy asks us to believe the cosmos is that second cyclist, propelled by an unseen tailwind. Before trusting the tail, scientists tug at the spokes of gravity itself, testing whether the old bicycle's frame might be bent. In the mountain recesses of Chile, the Dark Energy Survey photographs galaxies by the millions, measuring how their shapes are minutely stretched by gravity's pull. If space today obeys Einstein to the letter, the growth of cosmic structure should trace a precise tempo. But swap Einstein's field equations for a rewrite, perhaps a subtle function of curvature. Or a universe where gravity seeps into a hidden fifth dimension and that tempo drifts. Galaxies form too quickly or too slowly, like dancers missing the beat. Meanwhile, astronomers map redshift space distortions, the slight squashing of galaxy clusters along our line of sight caused by their peculiar motions. Too much squashing and gravity is overeager, too little in something else. Call it a chameleon force. Maybe shouldering the load, even tabletop labs join the hunt. Atom interferometer fountains toss rubidium clouds skyward, timing their falls to a billionth of a second, listening for hints of an extra tug or unexpected slack. Every new survey shrinks the hiding place for modified gravity. So far, the universe hums mostly in tune with general relativity, yet the unexplained acceleration remains, like a haunting refrain that refuses to resolve. If dark energy is a mirage, the only way to reveal it is to shake gravity's foundation and see whether the cosmos wobbles. Imagine hurling a paper boat into a broad river. Even after your hand lets go, the current carries the vessel farther each minute, destined for distant seas you'll never visit. Dark energy is that current writ cosmic, stretches the roots of photons, lengthens the timelines of future explorers, and redraws the very geodesics we once called straight. Voyager 1, racing beyond the heliopause, already feels the stage beneath it subtly widen. In a few trillion years, no matter how long its silent antenna waits, the Milky Way's neighbors will have slipped behind an event horizon of relentless expansion. For any civilization that follows, navigation will mean steering through a universe that grows faster than rocket engines can compensate, and plotting courses across a map whose scale bar lengthens as you read it. In our next chapter, Part 5, Weighing Shadows, we will place instruments, both earthly and orbital, upon this moving ground. We will see how new telescopes, gravitational wave sirens, and quantum sensors aim not just to watch the darkness, but to measure it. Kilogram by elusive kilogram, joule by whisper faint joule. Only then can we ask with any confidence, what destiny awaits a cosmos ruled by forces that hide their faces but command the stage? Dark energy doesn't merely speed the universe, it rewrites every future journey. And our best tools must learn to measure motion on a runway that lengthens beneath our feet.